Welcome, it's Paul with a script that explores the issue of generating points in regions within Rn using specified density functions. Now we know the theory behind this. If we have a function, which we usually call phi, from parameter space to our original space, and we want the density function to be constant in original space, then the density function in parameter space has to be the absolute value of the determinant of the Jacobian of the parameter function. So let's try this out. Our first goal will be to generate points inside the unit disk with uniform density. And here's a function that does this in a rather heavy-handed way. While true means keep doing this forever, except that we can get out of this while loop with return. So we generate a point in the unit square, that is, we generate two random variables uniformly distributed in -1 to +1, and if the sum of the squares is less than or equal to 1, then the point we generated is also in the unit disk and we return the value. Otherwise we go back and try again and again and again. See if this function works. The important thing, of course, is that it eventually gets out of that potentially infinite loop, and sure enough, it's generated a point where the sum of the squares is less than 1. Now let's do this 10,000 times. So we'll set up vectors x and y to hold the result. We will call the function, save the values in the ith components of x and I, and see what we've got. And when I do a scatter plot, it really looks as though we've succeeded in getting points all inside the unit disk, and not surprisingly, the density is uniform. Now, if we wanted to use polar coordinates, we could calculate the polar coordinate r, the square root of x squared plus y squared, a bunch of values all less than or equal to 1, and we can generate the angle theta. A fairly standard name for the function that does this is atan 2. This will give an angle in radians between 0 and 2 pi. And when we look at the histograms, we see, as we expected, the histogram for the polar coordinate theta is uniform, but when we look at the histogram for r, we see that the density is proportional to r. So that's a way of visualizing the fact that dx dy gets replaced by r dr d theta. And in fact, in parameter space, the density function isn't uniform. We can see that if we do a scatter plot of r and theta. You'll see in parameter space there are many more points when r is close to 1 than there are near r equals 0, and that makes good intuitive sense. Points where r is close to 0 give us points in the center of the circle. There's not much area there, so we want to suppress small radii. Now let's try a more challenging problem. That strategy of throwing away bad points doesn't work if the dimension of the manifold, 1 in the example I'm about to do, is less than the dimension of the space, 2. In other words, I can't generate points on the unit circle by generating points in the plane and throw them away if x squared plus y squared is different from 1. I'd end up throwing almost everything away. So here's the wrong way to do it. We want points on the unit circle, that is, we want a unit vector. So let's generate a point in the unit square and then divide it by its own length to produce a unit vector. When I try out this function, sure enough, I always get an x and y such that x squared plus y squared equals 1. Now let's do it 10,000 times and plot the results. Well, looks pretty good, doesn't it? The points are all on the unit circle, but it looks a little bit faint here and here, and a little bit heavy here and here. Let's plot the angles that we get by using the atan2 function, and I multiplied by 180 over pi to convert radians into degrees. So we're getting a bunch of angles. These are the polar coordinates of the various points we generated. And when you look at a histogram, you see what's gone wrong. Right near an angle of 50 degrees or minus 50 degrees, we're getting too many points. And when you think about it, that's obvious. That's heading off in the direction of one of the corners of the square, and we get more points in the square at those polar angles than at angles like 0 degrees and 90 degrees. How can we fix this? Well, there is a distribution at our disposal that is equally likely to generate a point heading off in any direction. That's the normal distribution. So, let's define a new function. This f norm generates two standard normal random variables and creates a unit vector from the results by dividing by the square root of the sum of the squares. We try this out. It looks much the same as before. X squared plus y squared equals 1. Let's do this 10,000 times and plot the results. Okay, not surprisingly, they're all on the circle, but we have to answer the question, are they uniformly distributed? We'll do that exactly the same way as before. Generate the angle theta for each point in degrees. Look at a histogram. This time it looks nice and uniform. Here's an approach that's better in general, though it can be a little bit tricky to figure out the functions you need. In this case, because we are using just one parameter, theta, and the Jacobian is constant, we can use a uniform distribution in parameter space. So let's just generate 10,000 angles uniformly distributed in parameter space. These are all in radians, which the built-in cosine and sine functions want, and because these trig functions are vectorized, we immediately get 10,000 x values and 10,000 corresponding y values. We do a scatter plot, and we get a gorgeous looking circle. Let's confirm that those are uniformly distributed the same way as before, and the histogram is uniform. However, I think eyeballing the scatter plot is not a particularly reliable way of checking uniformity. We can do better because these are standard calculations. If you have points on the unit circle that are uniformly distributed, the expectation of the quantity y squared, which is also the variance of y, should be 1/2, and sure enough, it is. A calculation that's done in almost every course in multivariable calculus gives us the mean of the absolute value of y. The physical version of this is usually you have a loop of wire in the form of a semicircle. What's the location of its center of mass? And the answer is it is distant 2 over pi from the center of the circle. If you want to think of this as a probability problem, you can say, consider points uniformly distributed on the unit circle. What's the expectation of the absolute value of one of the coordinates? And the answer is it's 2 over pi. Now let's do something more challenging. Let's look at a situation where the parametrization function has a non-constant Jacobian. We'll try to generate the complete unit disk. And first, let's do it wrong. Let's generate radii with a uniform distribution, and then compute 10,000 values of r cos theta, r sine theta, and plot it, and you can immediately see that something has gone wrong. The density is clearly greater in the center of that disk, and we know exactly what we did wrong. We wanted the density function to be uniform in original space, we made it uniform in parameter space, and the Jacobian messed things up. We can fix that. We need a density function for r that's proportional to the first power of r. And the beta function, the beta distribution, provides a way to do that. The first parameter for the beta distribution is 1 plus the exponent on x. So this will give us something that's proportional to x to the first power and to 1 minus x to the 0th power. If we look at a histogram for that, looks exactly the same as what we got before. And now we can generate points inside the unit disk using our parameterization function, r cos theta and r sine theta, giving x and y. If we plot this, well, it certainly looks like a uniform distribution, and we can verify this by checking some expectations. It's well known that the expectation of the random variable x squared plus y squared for the unit disk is 1/2. That came out right. A slightly messier calculation is the expectation of the absolute value of x or of y is supposed to be 4 over 3 pi, and that works too. Now let's do something really ambitious. Let's try generating points on the unit sphere in R3. This normal distribution trick, in fact, works in any number of dimensions. If you want to generate points on the unit sphere in R10, you can do it this way. All I do is generate 3 standard normal random variables, make them into a vector, divide by the length of that vector to make a unit vector. So now I have, as you can see, a 3-component vector where the sum of the squares is equal to 1. Let's do this 10,000 times. So now we've generated 10,000 points inside the unit sphere. We should not have favored any direction over any other direction. And some standard calculations. All these are going to be done either in lecture or in workshop or on the homework. The expectation of x squared plus y squared is 2/3. The way the physicists put this is they say the moment of inertia of a hollow sphere about a diameter is 2/3. That worked. And the mean of the absolute value of z, or of x, or of y should be 1/2. That works too. We can even try to graph the results. I found by browsing the internet a nice little package called Scatterplot 3D. This line is commented out because I have already installed it. If you want this, you'll have to run it. The nice thing about this is it is modeled on the plot or points function in ordinary R. There are fancier ways of doing 3D graphics, but they're not as straightforward as this one. So I try it, and well, it does look as though the points are heavily concentrated on the sphere. There's some on the front or the back, so there's no way that looking at this graphic will convince me that all the points are actually on the sphere. I can check, though, that a histogram of x squared plus y squared plus z squared gives us nothing but 1. So let's see if they're uniformly distributed. The two obvious parameters are longitude and latitude. So I can compute the longitude parameter theta by using the atan2 function. I've converted the longitudes into degrees, and if I look at a histogram, we clearly got that right. Now what about the latitudes? In order to do that, I need to take the arc cosine of z and subtract 90 degrees. That will give me something that's equal to 0 on the equator. That's our convention for the parameter phi. And if you look at a histogram of latitudes, you see there are a high number of counts near the equator, a small number of counts near the pole. And think about this. The fraction of the Earth's surface that is in between the equator and 10 degrees north latitude is much larger than the fraction that's in between 80 and 90 degrees north latitude. Now let's see if we can do this using parameters. When we parameterize the unit sphere with latitude and longitude, the density function is not constant. The density function has to be equal to the cosine of phi. So we've got a uniform density for longitude. After playing around, and I think I'm going to turn this into a problem, I found that if I generate uniform random numbers in 0 to 1, multiply by 2 and subtract 1, I get a random variable whose density function is proportional to the cosine of x. So this should generate longitude and latitude in accordance with the Jacobian. With the standard formulas, I can generate x, y, and z. And when I look at a scatter plot, it looks much like what we had before. A better check is the expectation of x squared plus y squared should be 2/3, and it is. And the expectation of the absolute value of z should be 1/2, and it is. Now for the final challenge. Let's see if we can use parameter space to generate a solid ball with uniform density in the original space. And you all know what the Jacobian is. It's r squared cosine phi. So we need a built-in function where the density is proportional to x squared. The beta distribution with the first parameter of 3 does just that, because this is going to give us something that's proportional to x raised to the 3 minus 1 power, proportional to x squared, and proportional also to 1 minus x raised to the 1 minus 1, or the 0th power. So there's a bunch of appropriate random radii. We already have our coordinates phi and theta. Let's crank out x, y, and z and see how we've done. If you're a physicist, you say, I know that if I have a uniform density ball of radius 1, its moment of inertia is 2/5. If you're a probabilist, you say, I know that for uniform density inside the unit ball, the expectation of x squared plus y squared should be 2/5, and it is. If you're a probabilist, you say the expected value of the distance of along any coordinate axis from the center of the ball should be 3/8. If you're a physicist, you say, I think I remember that the center of mass of a solid hemisphere is 3/8. And sure enough, we get 3/8. Finally, we can do a scatter plot of this, and it looks uniform to my eye, but I think those calculations with the expectation are better confirmation.